Up until this point, we've seen how we can use a vector valued function to draw a curve into space. Now, the way that we've done this so far, we've defined some r of t being some x of t, y of t in 2 dimensions, right? Or if it's 3 dimensions, you still get some curve that looks like this. Now, what's actually happening here, now this exists in an xy plane, but really there's a variable t here that's not showing up, and it's really a number line that goes from, say, A to B. And for each one of these t values here, it gets mapped to a vector up here. So t equals 1 might give you this vector. T equals 5 over here might give you that vector there. So each one of these t values is getting mapped to a vector here that's drawing a curve in the space. Now, you kind of think of a curve as a one-dimensional object because it's only moving in one direction, say t. So how do we draw a surface using parameters like this? Well, we're going to need 2 variables. Ooh, I need an eraser. We're going to need 2 independent variables instead of just 1. So we're going to find a parametric surface to be some r of u in v is going to be some x of u in v I, y of u in v j, z of u in v k. So notice here, each one of our components of our vector is a function of u and v. Now the concept here is in our 3-dimensional plane, let me go and draw this over here, we have an x, y, and z. Over here we have, just like we had our number line for t, we have what's called a uv plane, to where we're going to have some domain that u and v runs across. And for each point in this domain, this gets mapped to a 3-dimensional vector over here, just like before. Now this time, this vector is going to point to points on a surface. So each one of these points here gets mapped to a 3-dimensional vector over here. And if you map every point in this domain over here, we generally say that this is a domain or D, we get the surface on that side. So that's how we actually draw parametric surfaces get drawn. Now, how do we go from our normal rectangular to this parametric surface? A lot of times it'll be given to you, but how do we represent a, let's just say, rectangular function as a parametric function? So let's say if we had something like, normally like z is equal to x squared plus y squared, right? That's just our paraboloid one we've used 100 times. All right, it's pretty easy to do. You're thinking about this as here we have 2 independent variables. So define your vector value function u of r and v. Just let the x and y be x and y. So we're just going to replace them with here. So let's let it be ui plus vj. See, I let the x direction be independent because x is an independent variable up here. I let y be independent because it's a variable there. Now notice z depends on these 2 values. So the z component will be, well, we let x be equal to u, so it'll be u squared, plus we let y be equal to v, that will be v squared. Okay. So the easiest way to represent a rectangular function as a parametric surface or parametric function is let your independent variables be the new independent variables, and let the third one be the one that actually is defined by the function. So it's fairly easy to do. Actually, you don't have to do that very often. Well, I probably should kind of leave this up here just for a second. Let's go ahead and look at something else. How do we now, since we have this new idea of how things are being mapped from one place to the other, how do I now find a like a normal vector to a surface if we're given it in terms like this? Well, to find a normal vector, which we may use to like write the equation for a normal plane or a normal line, the idea is here. Here in this plane, the way you can kind of think about, let me get this out of here. At any given point, let's say that this point maps to the vector that points to the point on the surface here. If you think about this, we had two vectors moving in this direction, like this. You could say that this is the rate of change in the u direction, and that's the rate of change in the v direction. If you were to take both of these and map them over here, they're not going to necessarily point in a specific direction, but you could say that would be, say, r sub u. That's the rate of change as we move in the u direction. And some other vector up here would have to be r sub v, the rate of change as we move in the v direction. Now, it's not obvious from the way I have the picture drawn here, but when you kind of take these two and map them over here, these will actually be tangent to the surface. So if these two curves are tangent to the surface, if we want to find a normal vector, all we'd have to do is find the cross product of those two, like we did way back in 4 or 5 chapters ago. So a normal vector to a parametric surface will be, now I'm going to use the notation that this particular textbook uses, which again, I think he's breaking his rules. I'm going to use capital N here. We've already used that for the unit normal vector from the past. This isn't necessarily a unit vector though. It can be, but you wouldn't expect it to be. So all you'd have to do is r sub u cross r sub v, or r sub v cross r sub u. That would just give you the normal vector pointing the other way. So all you'd have to do is find r sub u. Of course, that's the derivative of this expression with respect to u. R sub v, find that. Let's take a look at one more thing. How could we find the surface area of this? Because we've kind of done it in the past, and I want to go ahead and use these pictures. We'll get some examples of these in a second. Remember the way that we found the surface area in the past? What we did is we found two vectors that formed a corner, kind of like r sub u, r sub v, and we said that that could make a very, very small plane right there, and that very, very small plane would be approximating that the area of the surface right there. Remember how we did this? We said that ds was the square root of 1 plus f sub x squared plus f sub y squared dA, and then we integrated across that to get that. Now this here was really just the area of that rectangle that we got by doing, remember it was the magnitude of, I don't remember what letters we called them, I think I called them u and v, where u was vector in one direction and v was the vector in the other direction. Well, that's exactly what we have here, except for now we say one is r sub u and one is r sub v. So to find the surface area, remember, surface area parametric, we did the area over the region that we were talking about of ds will now be the integral of, well, we're going to find the area of the parallelogram formed by those two corners. And what do we got to integrate that across? Well, we need to do that for every point in the domain that gets mapped over there. So we're going to integrate across the domain. And since our domain is an area, dA. All right, so we got a couple of formulas here. Let's actually take a look and see how these actually work out. So let's come up with a vectored value, a parametric surface. Let's make it an easy one. R sub u and v is equal to, let's do sine u cosine v, sine u sine v, and let's do, that would be cosine u then. Okay, so there is our parametric surface. It's still a vector valued function, but our parametric surface, because we have two independent variables. Now to show how much of the surface is being drawn, we have to give parameters on u's and v's. And this is actually going to define our domain. So let's let u run from 0 to pi, and v run from 0 to 2 pi. Now you may recognize these. I've changed the letters a little bit, but those are just the components for spherical. So this, if you replace u with phi and v with theta, this is actually a sphere if we let our bounds go all the way from that. So let's see if we can find a normal vector to the sphere. Well, the normal vector we know is r sub u cross r sub v. So what is r sub u? Well, we're going to take the derivative of each component with respect to u. So this will be cosine u cosine v. We're taking respect to u. So this is going to be cosine u sine v and negative sine of u. R sub v will be, now take the derivative with respect to v, negative sine u sine v. This is sine u cosine v and 0. That doesn't have any v's. All right, it's going to be kind of messy, but let's come over here and see if we can find the normal vector to this surface. So r sub u cross r sub v, I, j, k, gives us plenty of room here. So this is going to be cosine u cosine v, cosine u sine v, negative sine of u, sine u sine v, sine u cosine v, and 0. All right, let's start. In the I direction, that's going to be 0 minus, so that's going to be plus, sine squared u cosine v. In the J direction, so that's going to be 0 minus minus minus, gives me a minus. That's going to be sine squared u sine v. And in the K direction, let's see, what's this going to be? This times this, so this is sine u cosine squared v minus another minus. That gives me sine u cosine u sine squared v. All right, oh, in the K direction. All right, let's see if we can clean this up just a little bit. Can't really do much with the first two, so it's sine squared u cosine v I plus sine squared u sine v j plus, we can clean this up just a little bit. Notice if we factor out the sine u cosine u, we have a cosine squared v sine squared v. Of course, that's 1, so this is just sine u cosine u k. Okay, so this will give us the normal vector at any point on the surface of our sphere here. Pick a value for u, pick a value for v, plug it in, and that will tell you what the direction of that normal vector is. Now, what if we wanted to find the surface area of this sphere? Well, hopefully we already know what the surface area is, but let's see if we can come up with it in our formula, since we've already done a lot of the work. We saw from a minute ago that the surface area will be the integral over the domain, the magnitude of r sub u cross r sub v dA. Now we'll get to that piece in a second. Let's go ahead and find the magnitude of this, because this looks like there's going to be a lot of algebra. So the magnitude of r sub u cross r sub v will be equal to the square root of each component squared. So this is going to be sine to the 4th u cosine squared v, sine to the 4th u sine squared v, sine squared u cosine squared u. Okay, so again, let's see if we can clean this up. If we take a look at the first two terms, the first two terms here both have a sine squared u. If we factor that out, we'd have a cosine squared and a sine squared, which gives us a 1. So the first piece of simplification, the first two terms actually just combine to give me a sine to the 4th u, sine squared u, cosine squared u. Now again, if I factor, I'll write this one out. If we factor out a sine squared u, first one I'd have a sine squared u, and over here I'd have a cosine squared u. So this just reduces to the square root of sine squared u. Well, that's nice. Remember, that's going to give me the absolute value of the sine of u. Well, what do we know about the sine of u? Well, u runs from 0 to pi, so it goes from there to there, and we know that all students take calculus. So from 0 to pi, the sine of u is always positive, so I don't need these absolute values, so this is just the sine of u. Okay, so let's go back here. All we got to do now is take that argument. We need to integrate over the domain the sine of u dA. Now, what are these two pieces? Well, the domain, if you think about the domain as this region here, doesn't matter which one you call v, u goes from 0 to pi, and v goes from 0 to 2 pi. So what we end up is that's our domain that we have to integrate across. So this is going to end up being the integral of the sine of u, doesn't matter which one you integrate first, du, dv, or dv, du. We know in this region u runs from 0 to pi, v runs from 0 to 2 pi. All right, I need some room. All of this gone. All of that gone. All right, so the integral from 0 to 2 pi, the integral of sine of u is negative cosine of u. We need to evaluate that from 0 to pi dv. Top endpoint minus the bottom endpoint, so that's 0 to pi. That gives me negative cosine of pi minus the cosine of 0. Cosine of pi is negative 1, so that's negative 1, so that's 1 plus 1, so this is just to 2 pi. 0 to 2 pi of 2 dv, or 2 integral, 0 to 2 pi. Of course, that's just 2 pi, so we have 4 pi. All right, so is that the answer we were expecting? Well, remember, for a sphere, our surface area is 4 pi r squared. Now, by definition here, since our coefficients here are 1s, then our radius is 1 for that circle. If you put 1 in for r, you get, well, 4 pi. So, parametric surfaces are fairly nice to use sometimes. You notice, other than a lot of work to find this piece here, the domain's always easy to integrate across because you're always going to get a square for your two variables, or a rectangle for your two variables to integrate across, which makes the last piece fairly easy to do. We'll see parametric surfaces popping up again in the future.